discuss connectedness in directed graph. In case of undirected graph, if there is a path between every pair of vertices, it's called as connected. Now in case of directed graph, it's called as strongly connected. If there is a path from A to B and B to A whenever A and B are vertices in the graph. So you can say if there is a directed path between every pair of vertices, it's called as a strongly connected graph. For a directed graph to be strongly connected, there must be a sequence of directed edge from any vertex in the graph to any other vertices. Means there should be directed path from any vertex to any other vertex. Now definition 5, a directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. Means if we remove the direction and consider this as an undirected graph and there is a path between every pair of vertices, then it's called as weakly connected graph. So we can say every strongly connected graph is also weakly connected graph. Now example 7, at the directed graph G and H shown in the figure are strongly connected or weakly connected. These are G and H. Now check G. A to B there is a directed path, A to C there is a path, A to D there is a path, A to E there is a path, A to A there is a path. You can check for all pair of vertices there are directed path, hence G is strongly connected. As G is strongly connected, hence G is also weakly connected. If we remove the direction, there are paths between every pair of vertices. Now check the second graph. A to B, there are no path. B to A, there is path, but A to B, no path. Okay, even A to E, there are no path. Hence, this is not strongly connected as there are no directed path between every pair of vertices. It's weakly connected. If we remove the direction, then there is a path between every pair of vertices. But in graph H, B, C, D are strongly connected component. So this is a component where there is a path between every pair of vertices. H is not strongly connected, but this component B, C, D is strongly connected component of graph H. Now what is strongly connected component of a directed graph? The maximal strongly connected subgraph called as strongly connected component, or simply you can say strong component of graph. Now in previous example in graph H, B, C, D are strongly connected component. So in this B, C, D there are directed path between every pair of vertices. So this is strongly connected component. Next, path and isomorphism. I already discussed isomorphism. In case of isomorphism, we check whether two graphs are similar or not. We check some invariants like same number of vertices, same number of edges and same degree sequence. After that, if mapping possible, then two graphs are isomorphism. Now with this previous invariant, we'll add some invariant like circuit. So there are several ways that path and circuit can determine whether two graphs are isomorphism. The existence of simple circuit of particular length means both graphs have same length circuit, and that can be used as important invariant for checking whether graph are isomorphism or not. We can also take help of the path to construct the mapping for checking isomorphism. Now let's see one example. Example 9. Determine whether the graph G and H shown in the figure are isomorphic. These are the graph G and H. Now check all the invariant. Both graphs have 1, 2, 3, 4, 5, 6. 6 vertices and 1, 2, 3, 4, 5, 6, 7, 8. Both graphs have 6 vertices and 8 edges. Next we'll check the degree sequence. Here degree is 2, degree 3, degree 3, 3, 3, 2. Here 2, 3, 3, 3, 3, 2. So both also have the same degree sequence. 2 vertices have degree 2 and 4 vertices have degree 3. So now after degree sequence, we will check whether both have circuit of same size or not. Now in graph H, B1, B6, B2, there is a circuit of size 3. Now check in graph G, there are no circuit of size 3. There can be circuit of size 4. but no circuit of size 3. Hence, both graph G and H are not isomorphic as there are no circuit of same size. Here, number of vertices, number of edges and degree sequence are same, but as both have different size of circuit, hence both are not isomorphic. Now, next example, example 10, determine whether the graph G and H shown in figure are isomorphic. Both have same number of vertices 1, 2, 3, 4, 5. So both have 5 vertices and 6 edges. Next, both have same degree sequence 2, 3, 3, 2, 2. Here 2, 3, 2, 2, 3. So 3 vertices having degree 2 and 2 vertices having degree 3. Next, we will check the circuit. In H, there is a circuit of size 3, V1, V2, V3. Here also in G, there is a circuit of size 3. Here U1, U3, U4. And there are also circuit of size 4. Here V1, V3, V4, V5. So in graph G also there can be a circuit of size 4. U1, U5, U2, U3. And there is also a circuit of size 5. Here whole circuit size 5. Here also circuit size 5 is possible. As both graph have same number of vertices, same number of edges, same degree sequence and circuit of same size. So next we'll do the mapping. If mapping possible, then both graph are isomorphic. U1 same as V3. So this is our U1, this is V3, both have degree 3. Next U4 same as V2, this is U4, this is V2. U3 should be same as V1. Okay. So both have degree 3. Next U2 is same as V5, U5 same as V4. As mapping possible, we can map the vertices, hence both are isomorphic as all invariant matches in graph G and H. In today's lecture, I discussed connected, indirected graph, what is strongly connected, weakly connected, strongly connected component, path and isomorphism. How we can check two graphs are isomorphic by checking the circuit. In next lecture, I will discuss some more properties of connected graph. If this lecture is helpful for you, please like, share and subscribe. Thank you.